nuclear medicine all the time. And one of the things that he mentioned was really, I thought, good, was this. You basically take a 2 million count flood, with the detector in different positions, basically 90 degrees from each other. So this angular thing, okay, so you take a picture with it over the source, and then 90 degrees to the source, 180 degrees to the source, and 270 degrees. Okay? In all of these different positions, you should have the same amount of sensitivity and uniformity. Agree? In other words, the position of the gamma camera shouldn't affect its ability to detect radiation. And that's what this thing is saying here. 2 million count flood retained at 0. Record the time for the counts. So 2 million counts, and let's say 2000 K, let's say it took 60 seconds to do that. Okay? Additional images retained at 90, 100, and 270 using the time from the 0 image count. So you're going to do a 60-second count here, 60-second count here, 60-second count here. So I put down here, so for the 0 image took 63 seconds to get 2 million counts, then all of those in these other positions should be about the same amount of time to get the same number of counts. What would happen if we go over here and we get a 1,500,000 counts?
Something wrong.
Yeah, we've got a problem, don't we? Okay. If I get like 190 million counts here, I mean 190 or 1900, 1,900,000 counts. That's not too bad, but this is a fairly substantial drop in the number of counts. Okay.
Is it still 5%?
Yeah. Well, actually, it says 8, and then if you want, you can also take it should be less than 1%. Okay. 5% is a big number for this, so yeah, usually 1%. It's something that should get your head looking at.
What would cause such a problem for it to get less counts at a different position?
Well, sometimes the electronics will shift around in there. Sometimes, now one place discovered that they had background coming from the hot lab. So they changed positions. Yeah. So when the gamma camera was facing the hot lab, they were getting counts. Unfortunately, a lot of people don't bother to check the shielding of their hot labs. And so the thing was that it was affecting they just did this because they just had a lecture on it. We had a big thing on gamma camera quality control, and so as a result, they did this check, and when they found out that you have issues, you got issues. That's why I say, you guys, don't ever get complacent. Don't ever just treat this as, okay, it's just a job, and I'm just going to do the bare minimum to get through it. Okay. Then the other thing is, with your spec images, you should also buy one of those phantoms and take a picture of the Jazic Phantom. Have you seen those? Let me see if I can. Let's get a picture of one in here. Almost lunchtime, folks. We'll get you. trying to remember, which is the better, Google?
Oh, yeah. You know what they say, right? If you can't find it in Google in 3 minutes, it doesn't exist.
Okay, well, hopefully I'm, okay, Google search. These phantoms are not cheap, so. They have phantoms that you can use for calculating ejection fractions and things like that. Come on, nobody does nuclear medicine phantoms. Let me just take a look here at one of my books here. I know that it's in. Okay, this is a Jazic phantom here. Okay, basically it looks like a thyroid phantom, but it has all these little balls in it, different size. Have you seen it?
No.
Did they ever use it?
How much is that?
I don't know. They're not cheap. I know that.
You couldn't find that online?
No. Okay, but you can either fill the balls with radioactive material and take a picture of it, or you can fill the whole phantom with radioactive solution, and then the balls displace it, and then you look at it that way. And the images will look something like this. Okay, so that's what you're basically testing, is the instrument's ability to visualize the little small objects in there. So sometimes they have it as a hot tumor or a cold tumor, and that's what you're looking for. Okay. And then the other thing that they do, I haven't, because MUGA studies aren't that big of a thing anymore. When they first came out, we thought that was, a great way to analyze the heart ejection fraction and look at wall motion. Now we typically only do it for patients that are getting chemotherapy, methotrexate. And so anyway, before they start them on that type of chemotherapy, they'll do a MUGA study, and then they'll kind of follow them up to make sure that the chemotherapy isn't damaging the heart. But they do have a phantom that you can buy where it simulates a certain ejection fraction, and so you take a picture of it using your MUGA acquisition, and then if you have it set for 60% and your ejection fraction comes out something different, then you can start, having problems or looking at.
How much is that phantom?
That's expensive. Those things are like $5 grand,
Will you fill it up with tech?
Yeah, you put tech in it, and
that's how you know for sure your camera is really. But isn't that kind of like calculations too, like drawing around the ventricle?
well, here, this is a MUGA study here. You guys probably won't see too many of these. But one of the things we were talking about, ray paths. Okay, remember, here's your right ventricle, here's the septum, and here's the left ventricle. Normally, what is the best picture to separate the right and left ventricle from each other? Yeah, about a 45 LAO. And some people even angle it 5 degrees Quadrad or whatever. Okay, but the thing is this. If you put it on auto detect, the computer is going to search out the pixel that has the highest number of counts. And then it's going to send out ray paths in 64 different directions. Okay? And the count rate stays up pretty high, and then all of a sudden it gets to the edge of the heart, and then it drops off dramatically. Okay, what they could do is they call that the second derivation of the slope. Okay? So in other words, if you remember calculating the slope, if you compare the number of counts in each one of these pixels, there's not a big difference. But when you get to the edge of the heart, you know, all of a sudden, like you might have 1,000 counts here, but then you get to the edge of the heart where there's 500, or let's say that there's 750. Okay, so the slope would be 250 counts. So as soon as the computer detects 750 counts minus 250, so 500 counts, it says, okay, that's the edge of the heart. Okay. So here you see it has end diastole and end systole regions of interest. Well, actually, I think this is probably wall motion here, because here's end systole, here's end diastole, here's a background area out here. Here's the ejection fraction. This is what they call the velocity curve. So you can actually get an estimate of how fast blood is being pumped. You can also get an idea of the volume of blood that's being pumped. Okay. And then over here, okay, here's your regional ejection fractions. So basically, what's the normal ejection fraction, by the way? How much?
50%.
Yeah, about 50 or 60. An ejection fraction of 81, I get really worried about that. That's almost unbelievable. And this usually happens when you have mitral valve problems. You know, in other words, when the heart contracts, you know, blood gets pushed back into the lungs and out into the body. I mean, I have never seen an ejection fraction that high or a ventricle that small. So I kind of have my, I don't know about that even. Okay, but then again, so this is what they call a regional ejection fraction. So you can actually analyze the individual. They break it up into usually like 8 pictures. So here's 1, 2, 3, 4, 5. So we're missing some other pictures there. Because remember over here on the septum, you don't really get a lot of motion, right? The septum doesn't move very much. And then over here, they have what they call phase analysis. Have you ever heard of that before? Did you ever see this on your pictures? Phase analysis is one of what they call functional imaging things that we do. Basically, as the heart contracts, you should see the pixels change at the same rate. So in other words, as the heart is compressing, the number of counts should be uniformly changing at the same rate. And if you don't have that, then a lot of times that's an area where the tissue has been damaged. You've had an infarct, or you have what they call a pseudoaneurysm. So what they're showing you here, this is what they call phase analysis. If there was any part of the heart that was not beating in phase, so in other words, what am I looking at here? Okay, this would represent end diastole, this would represent end systole. So if I saw any black marks in here, that means that that part of the heart is beating out of phase. It's what they call paradoxical motion. Paradox means that it's doing the opposite of what it should be doing. So instead of contracting, it may be bulging out. And that's typically what happens when you have a myocardial infarction. The scar tissue bulges out at that area where the injury occurred.
Is that the whole heart or just the left ventricle?
This is the left ventricle here. This is the right ventricle. Superior vena cava. And what I'm hoping, you know, like normally the ventricles should be in phase with each other, so the 2 ventricles contract at the same time, the 2 atria contract at the same time. So if there was anything other than that, okay, that means you got a problem. But we're going to be talking about mugga studies and heart studies here pretty soon, so in fact probably starting next week. Okay. So, with that happy note there, okay. The other thing that is of importance as far as spec images can be found in your math book. On page 138 of your math book. Okay. Sometimes we go for a certain amount of counts, which is obviously what we should be trying to do, but sometimes we only go for a period of time. So we need to estimate approximately how many counts are we going to be obtaining with that. So, let me just open this up a little bit here. They will be giving you questions about this on your board exam, so that's what I want you to be prepared for that. So it says, when referring to spec projections, the terms stop, steps, or frames may also be used. Okay, and then notice on here, the acquisition time, you multiply the number of projections times time per projection. So if you have 64 projections of 30 seconds each, basically 64 times 30 seconds, and you're looking at about 30 minutes, right? Or 32 minutes.
Plus the time it takes the camera to move.
Yeah. Well, they don't take that into consideration. Okay? Or the other way that you do it is if you tell the computer you want 2 million counts, okay? So basically you take the count rate, you know, your gamma camera will typically tell you what the count rate is. So if it's like 10,000 counts per second, and you're going for 2 million counts, so basically 2 million divided by 10,000 counts per second will tell you how many seconds. Yeah, something like that. So 200 seconds. And the other thing is that the time per projection. Okay. And again, if you know that it's going to take 30 minutes and the number of projections, these are just all variations of the same math formula. You know? So I don't want you to, when you see this, I don't want you to panic and think, oh my God, this is, how the heck am I ever going to be able to calculate this? It's usually going to be one of these three variations here. Like what is the total counts per projection, or, you know, the time per projection and the counting rate. So, as I said, this is something that you can expect with your for spec questions that you'll see on your board exams. So notice it says 3 million count spec studies to be performed on a phantom that produces 200,000 counts per minute. If there's 64 steps over 360 degrees, what is the total time of this acquisition? Time per stop and counts. Okay, well, again, this is a real simple way to do it. 200,000 counts per minute, 3 million counts, it's going to take 15 minutes. Time per projection, 15 minutes divided by 64 stops. You know, some people like to play with this, like they'll, instead of 0.23 minutes, they'll say, how many seconds is that? Some people you might know who are very near and dear to your heart. would ask you a question like that. And then the counts per projection. Okay. So, you see what you're in for with this? Yeah. Oh, boy, howdy. I can get a couple of good questions with that, real easily on that. Okay, so that's page 138, 139, and also on 140. There was a little interesting comment that I saw down here too that you might want to take a look at. It says the difference in total counts for the acquisition using the two methods is insignificant. It's usually less than 3%. Either method is valid as your opinion, a reasonable estimate, not a precise number. Because, as Mr. Viat pointed out, the time that it takes for the camera to move to the next step is not taken into consideration here.
I'll take the credit.
Oh, I'm sorry, Mr. Andy said that. Okay, so you might want to take a look at that. You might want to work a few of these problems here because, as I said, sooner or probably sooner than later you'll be seeing this on a little quiz. Okay, so with that being said, I can see with the lights shining out of your eyes, you're full of knowledge right now. So why don't we send you to lunch?